Hey everyone, it's calculus time, and today we're going to be taking a look at the extreme values of functions. That's extreme values, so you might be thinking, well, what does that mean? We're going to take a look at that. And our framing device for this chapter, it's going to be zombie movies. So one zombie movie that I kind of enjoyed a lot was this Zombie 2. It was a 1979 zombie film. Directed by Lucio Fulci, adapted from an original screenplay. And it was supposed to be a sequel to The Dawn of the Dead, which was a really famous zombie movie, which you may have heard of. But it is an Italian film, so the original title was Zombie, I suppose. So this is zombies in the Caribbean, and there is a very much a tradition there with Caribbean zombies. So as we come down here, this is actual math stuff. We've got absolute extreme values. So the absolute maximum value of f of x is where f of x is less than or equal to that number for all in the domain. Basically, it is the highest point, or at least tied for the highest point. The minimum is kind of the same thing. It's the opposite, where it is the lowest point, or the y-coordinate is smaller than all the other y-coordinates around. So this first one over here, this first question we got is examining the graph of this graph right here. This is the graph of y equals cosine of x. Y equals cosine of x. So we want to visually determine where the maximum and minimum values are. Remember that the extreme values are actually y-coordinates. Now, if this is our function, then it shouldn't be too difficult to see that this right here, that's a maximum value. And really, there are two minimum values. There's one right here, and there's also one right here. Remembering, of course, that the domain that we're going to be talking about is from negative pi over 2 to positive pi over 2. To correctly respond to this, we have to say what is the maximum value and what is the minimum value. Well, these are the y coordinates. So the maximum value, the highest point, has a y coordinate of 1. And the lowest, the smallest y coordinate that we're going to see is going to be 0. So visually, that's not a big deal. And as you can probably expect, since it's not that big of a deal, this is, not the level of questionings that we're going to be expecting in calculus. But if you don't get the idea of what it means to be a maximum or minimum, then you don't really understand this problem. So let's keep on going with this, and we see domain and extreme values. And the domain makes a real big difference on what those extreme values are. We saw a little bit of that. Now, here we have the function x squared minus 2, right over here. This is x squared minus 2. And we're supposed to figure out what are the minimum and maximum value for the following domains. Well, the first domain that we're going to be looking at is negative 3 to 1. Now, domain is the x coordinate. So here's x equals 3, and here's x equals negative 1. So we're talking exclusively about this little bit of the curve right here. Okay, so visually, what is the maximum y coordinate of that curve? And that's just right up here. There's our maximum. That looks like about 6 or so, no, 7. Y coordinate of 7. And where's our minimum? Well, that's not there, but right down over here. It's gonna be hard to see. Hold on one second. Looks like our minimum is right here. I think that is y equals negative 1. Perfect. Our minimum value is y equals negative 1. Our maximum value is y equals 7, although we don't say y equals, we just say negative 1 and 7. How about from negative 3 to 3? Okay, so from negative 3 to positive 3 would be all of this right here. Okay, so this looks like the maximum value is this y-coordinate, which looks like 7. And our minimum would be this y-coordinate down at the bottom, which looks like about y equals negative 1 again. So I'm thinking this is about the same thing. And of course, when I said negative 1, I probably meant negative 2. All right, so that's from negative 3 to 3. Now here's a tricky one. Take a look here at these endpoints. They are parentheses instead of brackets. And that means to us that our coordinate is never going to actually reach negative 3, and it's never going to actually reach positive 3. So let me show you what I mean. If I'm coming from the left here, what is the y-coordinate? Well, right now the y-coordinate is 2, and then now the y-coordinate is 3, and now the y-coordinate is 4, and now the y-coordinate is 5, and now the y-coordinate is 5, 5.5. No, that's 6. I'm sorry. Well, then we get to 5.5, and then we get to 5.75, 5.8, 5.9, 5.99, 5.999, 5.9999. You can see where we're going here. We're never actually going to get to a y-coordinate of 7 because the function is not defined at x equals negative 3. So what that means is we're not actually going to have a maximum. Like if you say the maximum is y equals 6.99, well, actually the function can get to 6.999. And what about if you said the maximum was 6.999? Well, actually the function can get to 6.9999. So you can just keep on getting closer and closer to 7 without actually getting to 7. So that's why we say there's no actual maximum value. The minimum value is the same. It's still negative 2. So if that maximum of value occurs at a place that is not part of the interval, or would have been a part of the interval, then the maximum value does not exist. So it's very possible. This happens when you have a hole. This happens if your maximum value happens at a hole. This happens if your maximum value happens at an open endpoint. Okay. Same thing's true for minimum value. If your minimum value is at a hole in the graph, then the minimum value doesn't exist. And if the minimum value occurs at a endpoint that doesn't exist, an open endpoint, then that minimum value is not going to exist. So what about where the domain is from negative infinity to positive infinity? Well, the minimum is still going to be negative 2. I think we can see that right there. But the maximum value, for a different reason, the maximum value is not going to exist. Because now the y-coordinate does get bigger and bigger in the sense that we like to think of it. So it goes from 100 to 150 to 200. You can always get a bigger number in the y-coordinate. You just have to put in a bigger value in the x-coordinate. So here, the minimum value is negative 2, and the maximum value is does not exist. Whenever you need to write does not exist in this class, you can just write D-N-E, and that's does not exist. So now's probably a good time for us to talk about absolute extrema. And when we were looking at this previous graph, in order for us to figure out, if our domain was all real numbers, in order to figure out what was happening on the left and the right, we had to know a little bit about the function itself. So endpoint behavior, this is just kind of a rundown of endpoint behavior for a polynomial function, and this is kind of handy. Even polynomials, as x goes to negative infinity, the y-coordinate goes to positive infinity. Minimum, yes, it has a minimum, does not have a maximum. Opposite's true. If the lead term is negative, then the polynomial will go to negative infinity to on the left side and negative infinity on the right side. There's no minimum, but there is a maximum. And if you have an odd polynomial, then the odd polynomial with a positive lead term, that's going to go to negative infinity on the left, positive infinity on the right. Opposite is true for an odd function that has a negative lead term. It's going to go to positive infinity on the left, negative infinity on the right. In either case, an odd polynomial does not have an absolute maximum or an absolute minimum globally. Okay, so moving on from here, we're going to take a look at the next one, which is local extreme values. And the idea for a local extreme value is that for a local minimum or local maximum, which oftentimes we call a relative minimum or a relative maximum, it just needs to be the highest point or the lowest point in its neighborhood. In other words, there are points directly to the left and to the right which are higher or lower than there. So let's take a look at the first one. There's some marking rules here, which I'm just not going to really talk about, but we'll take a look at the first one. Over here, we have a relative maximum, and we call that a relative maximum or a local maximum because if any endpoint, any interval that contains that diamond location is going to be the maximum of that interval. For example, if I do an interval like this, where that diamond is kind of near the, an interior point, then yeah, that's the highest y coordinate. But it doesn't even have to be an interval like that. It could be an interval where that diamond is at the right side of the interval. In this interval, that diamond is the maximum value. How about this one? If I draw it on the other side. Okay, an interval on the other side, again, if it contains that diamond point is going to be the maximum interval, the maximum y coordinate. So we call that a local maximum or a relative maximum. Any interval that you draw that contains that coordinate, we see down here that coordinate is d. So anything that contains d will have d as the absolute maximum. Is there another interval, or is there another absolute maximum? Yes, there is. Right over here at C. At C, we can see again that any interval you draw that contains C will have C as the absolute maximum of that interval. How about minimums? So we're going to start off with a controversial one over here. This endpoint, that actually is an absolute minimum. Again, if you can, any interval that you make on this domain that contains point B, point B will be the minimum. Are there other relative minimums? E and A. Both of those are relative minimums because if you include them on an interval, they will be the minimum point. Now, on this interval, can we figure out what is the absolute minimum value? What is the lowest place, the smallest y coordinate in this interval? It's point A. How about the absolute maximum, the highest point in this interval? And yeah, that's point D. Usually the absolute mins and the absolute maxes, those, people have a little bit less trouble with those. So there is absolute minimum, absolute maximum, local minimum, local maximum. So now we can get into a couple of definitions. So the first place is the idea of a critical point or a critical value. So a critical point is an interior point of the domain at which the derivative is either equal to 0 or the derivative does not exist. This is an incredibly important definition for you guys. Any place on the interior where the derivative is equal to 0 or does not exist is called a critical point or a critical value. In my head, when I see critical point, I think about the x and y coordinate. And when I see critical value, I think of just the x coordinate. Okay? Well, we can actually divide that up again into another idea of a stationary point. And a stationary point is a critical point where the derivative is equal to 0. Now, we don't use the vocabulary of stationary point very often, but you may want to keep that, in the back of your hat, just in case someone pulls out the stationary point. You know that is a place where the derivative is equal to 0. So, critical point, derivative is 0 or undefined. Stationary point, the derivative is exactly equal to 0. Okay, we're going to scroll down to one of the most important tools here on calculus, and it is the candidate test. So I'm just going to read along with you. I know you know how to read, but I'm going to do it anyways. Finding the extreme value of a function on a closed interval is a task to which the techniques of calculus is well suited. Since the extreme value of a function must be located at a critical point or at the endpoint of an interval, we only need to test these candidates, critical points and endpoints, to locate extreme values. So I'm going to say this again. If the task is to find the extreme value of a function on an interval, then you're going to use the candidate test. So we have this example. We've got the volume of a box is modeled by this equation. Volume is equal to x times a quantity 10 minus 2x times a quantity 16 minus 2x, where x is the height of the box and x is between 0 and 4. So the first idea here is, well, let's find the derivative of the volume. Well, that's not too bad. We're going to take the function and we're going to expand it to make it easier to take a derivative. That's what we have here. 4 times a quantity x cubed minus 13x squared plus 40x. And then we're going to take the derivative of everything. Now we're going to keep the 4 on the outside. The derivative of x cubed is 3x squared. The derivative of 13x squared is 26x. And the derivative of 40x is just 40. So we've done it. We have found dv dx. And that's always the first step to the candidate test. Next part, we're going to use the equation in part A to locate all the candidates. Now remember, there are two things here. The candidate is the place where the derivative is equal to 0, or if the derivative is undefined. Now, the derivative is undefined. That means those are places where the denominator of the derivative is equal to 0. And we'll certainly take a look at those also. So here we go with our derivative. We've gone ahead and we've factored it a little bit. We've got 3 times the quantity 3x minus 20, and x minus 2 is equal to 0. Your experience with factoring is going to be helpful here. And then we're going to set that derivative equal to 0. So it looks like, based on the factors here, we have that 20 over 3, or x equals 2. Now, do any of those coordinates sound funny? Yes. 20 over 3. That simplifies to 6 2/3. 6 2/3 was not in our interval of 0 to 4. So actually 6.6 is not a critical value that we're going to test. Okay. Now, what about the endpoints of the interval? The endpoints of the interval were 0 and 4. So it looks like we have ourselves three different candidates. The first candidate is 2. The next candidate is 0. The last candidate is 4. And all we have to do is check the volume at those three candidates. So part C, evaluate the volume of the box at all the candidates in part B. What is the maximum value? Right, the first thing we're going to test, okay, at x equals 0, you see us evaluating here. We've got 0 times 10 minus 2 times 0 multiplied by 16 minus 2 times 0. That is the original volume function from up here, just factored. And that gives me 0. What's the next volume function? Okay, the volume in x equals 2 is 144. And then the volume when x equals 4 is 64. So from those three candidates, what is the maximum value? What is the maximum volume? Okay, so the maximum volume clearly is 144 cubic units. Okay, so here is our candidate test. Step 1, find the derivative. Step 2, solve for all the candidates, which are endpoints and critical values. Number 3, evaluate the candidates for the function you're trying to maximize. Now, the common mistake here is people take the derivatives and the endpoints and they substitute them back into the derivative. No, no, no. You already know the derivative is going to be 0, or the derivative is going to, or it's going to be the derivative at the endpoint. And you're not trying to maximize the derivative, you're trying to maximize the volume. So you substitute into the volume formula. Testing an open interval or a half open interval, you're going to have to know the end behavior and critical points to find the actual maximum and minimum values. And that brings us to the end of this section with our important ideas. So the important ideas, the first one we have is local extrema. Local extrema is the highest and lowest point in the immediate neighborhood. That's usually the easiest way to figure it out. That's not a very mathematical definition. A mathematical definition would, of course, be a local extrema is if a point is a local extrema, then any interval that contains that point will have that point as either the highest or the lowest point. Absolute extrema would be the very highest point in that interval. You can have many local extremas, but you can only have one absolute extrema unless the absolute extrema doesn't exist. What is a critical point? Critical point is an interior point of an interval where the derivative is either equal to 0 or the derivative is undefined. Stationary point is an interior point where the derivative is exactly equal to 0. And the candidate test, well, that means the extreme value must occur at the endpoint or a critical point. So those are the only points that need to be considered. I'm sure in class you're going to have a list of those 3 steps to find a candidate test. So let's go ahead and list them out. So for your candidate test, you need to find the equation of the derivative. Number 2, you want to solve for the interior critical points. And number 3, you want to evaluate the equation at all candidates, the interior critical values and endpoints. And then I suppose you should identify the extreme value or values. Okay, so scrolling from here down at the bottom with our check your understanding, we're supposed to find the extreme values of 1 over the square root of x squared plus 1 for x between negative infinity to positive infinity. So this is a global extreme. Now there's a couple of things that are interesting about this function as I'm looking at it. The first thing I'm going to take a look at is our denominator is always going to be positive. And I can tell it's always going to be positive because, well, it has a square root, and that square root always gives me a positive result. So it doesn't matter what number I can put in there for x, I'm always going to get a positive number. Also, the domain here is going to be all real numbers because the only x I see is inside the square root, and it is squared. So it doesn't matter what number I substitute for x squared is always going to be positive, and I can always take a square root of a positive number. So that's an interesting thing. We always have a positive result. Well, let's do our thing for extreme values. So first thing we're going to do, take our derivatives. We're going to find our candidates. Now, you might be saying, why am I saying candidates? We're on an open interval. Well, we can still look at the candidates for things like for this. The extreme values have to occur at a critical value or an endpoint. We can't evaluate the endpoints directly, but we can certainly infer what the behavior is using limits, which we'll see that in a minute. So here's our derivative. What is the derivative of x squared plus 1 to the negative 1/2 power? So we take the negative 1/2 and we drop it in the front. We leave the x squared plus 1 alone, leave the base alone. We decrease the power by 1. Negative 1/2 minus 1 is negative 3/2. And then we multiply by the derivative of the base. What is the derivative of x squared plus 1? It's 2x. And then we simplify that and we get negative x over the square root of x squared plus 1 cubed. So we're going to look at two things. And I always love to see the derivative as a quotient like this. It makes finding a critical number easy. So let me rephrase that. If the job here is going to be to find a critical number, then you want your derivative to look like a quotient. So when is the numerator equal to 0? At x equals 0. When is the denominator equal to 0? Well, that denominator will never equal 0 because x squared plus 1 is never going to equal 0. So the next thing for us to figure out is what are the y coordinates at this critical value, and what is the behavior of the function to the left and to the right? So we can do that easily by taking a look. Well, what happens when x equals 0? Well, when x equals 0, the function 1 over x squared plus 1 is just equal to 1. Okay, that's nice. Now we're going to talk about the endpoint behavior. What happens when x approaches negative infinity? What happens when this goes to negative infinity? Well, if x goes to negative infinity, the denominator keeps on getting bigger and bigger. Now that's something that is going to show up time and time again in calculus. We want to see what happens here. Does it get bigger? Does it get smaller? What happens? And as it turns out, x squared plus 1 gets bigger and bigger. 1 over a really large number approaches 0. So as x approaches negative infinity, this function is going to approach 0. And of course, that value is never going to be reached. As we get to negative infinity, the y-coordinate will get closer and closer to 0, but it will never be actually exactly equal to 0. Same thing as x approaches positive infinity, this denominator gets bigger and bigger and bigger. 1 over a really large number is close to 0. And you might want to think about 1 over 100, 1 over 1,000, 1 over 10,000, 1 over 1,000,000. We're talking about really small numbers. And because that is in the denominator, that value is also never reached. Okay, so we never reach the minimum value of 0. We can reach the maximum value of 1. So we can say that the absolute maximum is going to be 1 and the absolute minimum is going to be does not exist. Now, if we had multiple critical points, we would have had to have tested them to see which one was going to be the absolute maximum or the absolute minimum. But as it turns out, we're okay on this one. So that's the end of what we're doing here today. Our really brief look at minimum and maximum value and behaviors. We'll see you next time here for more calculus.